Okay, so we're looking at this idea of trying to work out the average separation of stars in a cluster. So this is a bit of an aside, and probably not something I'd normally ask in the module, but it gives us an interesting insight into these clusters. So, as I mentioned, the first thing to do would be to work out the number of stars per cubic parsec in this spherical volume of the cluster. So again, we can just do n over 4 pi r cubed here to give the, so this is like a number density. Okay, so it's a number per unit volume rather than a normal mass density, which is a mass per unit volume. So this can be a very useful concept in many areas of physics. So we've got 10 to the 5 stars in this volume. So if you work the numbers out like that, it turns out to be about 24 stars packed into each cubic parsec. Okay. So the trick here is to sort of think about, if each star is separated from the next one by the same length, so I'm just calling that x here, you can think about the sort of typical volume around an individual star then would be x cubed, okay? And then there's so many of those little cubes make up the entire volume. So using that kind of concept, you can see that if we just turn this number around, so we just need to do 1 over the cube root of this number density, which is in stars per cubic parsec. You think about the units here, and quite often the units point the way to what you should do, then that is going to come out to sort of parsecs per star, if you know what I mean. Okay. If you do this mathematical operation, so if we do that, then it's going to come out in dimensions of parsecs, and this would then be a typical type of separation between each star. So again, you could reverse that argument. If you worked out the volume of a cube, 0.3 parsecs on a side, and multiplied it by 10 to the 5, you'd end up back with your sphere of 10 parsecs radius again. So that's another way of thinking about it. Okay. So recall that, for us here on the Earth, our nearest star, Alpha Centauri, is about 1.3 parsecs away. So you can see that this separation is already 3 or 4 times more. Well, the stars are already 3 or 4 times closer together than they typically are where we live in our part of the galaxy. And of course, we've already done an average over an entire volume here. So you can see that on the outer parts of the globular cluster, then they're not very well packed in, but in the center, they're really, really well packed in. So actually, in the center of these globular clusters, the typical separations are much smaller than this. And they can get quite interestingly small, so that stars can actually sort of interact with each other, maybe not exactly hit each other, but in the middle of there, you get some pretty weird objects due to stars interacting with themselves, well, with their near neighbors. But let's not digress too much. Okay, let's come back to another interesting issue that I want to bring into this, because it's illustrated nicely by these 2 types of clusters, the open clusters and the globular clusters. So this is another aspect of evolution. So rather than how stars just sort of evolve in their parameters in the HR diagram over time, what happens over a more, over the real whole history of the universe, if you like, in terms of the chemical makeup of stars. So this is the field of the chemical evolution of the whole universe, really. But obviously we trace it through the makeup of the stars in there. So again, we're going to talk about a little bit about the idea of the universe starting with a Big Bang later in the module. A little bang there. So again, you'll have to sort of take some of this from me for the moment, that the universe started with this Big Bang, with a big fireball of gas that was expanding and cooling, and basically the first stars formed out of that material that was cooling down from the original Big Bang explosion. And the only elements that we believe were in that gas that made up the Big Bang was just hydrogen and helium, so the two simplest elements. And again, these are predictions that come out of the theory of the Big Bang, and they hold up extremely well to observational scrutiny. So that, you know, the 75% hydrogen, 25% helium was pretty much set in stone from the Big Bang itself. Okay. Now, obviously, stars are turning hydrogen into helium over time. So the amount of helium in the universe will grow over time. But they're not just making helium. You know, the heavier mass stars, the high mass stars, are making all sorts of elements, all the way up to iron. Okay. So they will be making the carbon and the nitrogen and the oxygen as well. And some of the lower mass stars will make carbon, nitrogen, oxygen. But then the massive ones will make iron as well, all those kind of elements. Okay. So this process is referred to as nucleosynthesis. So it's operating on the nuclei. Okay, you're fusing nuclei together and you're synthesizing new elements. Okay, you're turning hydrogen to helium and then turning helium into carbon, etc., etc. So stellar nucleosynthesis is the process by which the material that makes up the universe is enriched due to nuclear fusion going on inside stars. But we have then seen that at the end of a star's life, whether it's a low mass star that ejects its envelope as a planetary nebula, or whether it's the much more explosive supernova explosion at the end of a massive star's life, both of those processes end up returning basically chemically enriched material back out into space. Okay, so the star will have started off like a star, you know, made out of the very first stars, will just have been hydrogen and helium. But at the end of their lives, they will have made some more helium and a whole bunch of other heavier elements. And that material that is now enriched in those heavy elements will have been returned out into space by the processes at the end of a star's life. So just to remind you again, here's a picture on the left. This is again, picture of a supernova remnant. So the kind of an explosion will have happened in the middle here, and you've got these shock waves going out through as material just gets hurtled out into space. So the material hurtling out here is enriched, especially in iron from these massive stars. And the more gentle processes that will happen at the end of the sun's life is that this material, again, is slowly moving away from the star. But again, it's enriched in helium and carbon, nitrogen, oxygen, those type of elements in these lower mass stars. So these returning processes are taking chemically enriched material and putting it back into space. Now, that material that then is floating around in between the stars, as we will refer to it as the interstellar medium in future lectures, is the raw material for the next generation of stars. The whole way galaxies operate, there's this continual cycle out there of material that is collapsing under gravity. These clouds in between the stars are forming a new generation of stars. You get stellar nucleosynthesis going, and then at the end of that generation of stars, that material is returned and it's even more enriched in heavier elements than when it went in. So get this idea in your head of successive generations of stars that become progressively more enriched in the heavy elements. Now, I'll also introduce a little bit of terminology here that astronomers tend to use. They get a bit lazy when they're talking about different elements. So in the astronomer's world, there's usually hydrogen, 75%, helium, around about 25%, And then everything else that's heavier than helium is usually referred to as a metal, even though clearly a lot of the elements aren't actual metals. So things like carbon and nitrogen and oxygen are also referred to as metals. And we shall see that that also leads to the term metallicity as well. You will see that term. But basically, when you see the term metal in astronomy, it's a shorthand for all elements heavier than helium. Now, how do we know that this chemical enrichment is happening out there in space and over cosmic time? Well, we can measure the composition of stars by looking at their spectra. Okay, so I showed you spectra of stars a couple of lectures ago. At the time, we were using them to work out the surface temperature of the star. But once you've worked out the surface temperature of the star, and you've got an idea of the luminosity class, so you know the density of the material. If you know the temperature and density, you can then, and you know the atomic physics, so you know how strong those spectral lines should be intrinsically, you can actually use all of that information to work out the composition. So how much carbon, nitrogen, oxygen, iron is in the atmosphere of the star you are looking at. So if you can find stars that are different ages and represent different generations, so when were these stars actually formed, you've got a way of then tracking the buildup of elements over time in the universe. So this diagram summarizes this. Okay, so here's an example of, again, two photographic spectra of two stars. This time, again, they are both exactly the same spectral type. So they're both the same temperature. They're also actually the same luminosity. You can see the widths of the lines are exactly the same. But there's a big difference between the spectrum on the top and the spectrum on the bottom. So you can see that their hydrogen lines are very similar. Okay. But all the other lines, they're present in the top spectrum. You can see them. They're just very faint. Okay. So these two stars are the same temperature. So the difference in strengths here is nothing to do with nothing to do with temperature. And it's nothing to do with luminosity because they're the same as well. So the only difference here is that the abundance of all the heavier elements, heavier than hydrogen, as you can see in the spectrum, is much lower in the top spectrum than in the bottom one. Okay. You can see in the caption here that there is some new terminology here about populations of stars, and so that's what we're going to discuss next. So again, this is a sort of a broad brush division of stars into two groups. So I'm going to describe the properties of population 1 stars first. So basically we have population 1 and population 2. You see this terminology in astronomy a lot. Okay, so what are the characteristics of population 1 stars? So they are young, and if we want to quantify that, then less than around about 1 billion years. So anything from over 1 million or 10 million here up to 1 billion years or so would be considered a sort of a young population of stars. I know it sounds old, but you need to get used to sort of thinking about what's old and what's young in terms of the whole universe. And the key new point here is that these stars, because they're young, so we don't mean young as in young in the age of the universe, we mean young as in they have formed recently. Okay, so again, just make sure you get that clear in your head. So a star that we see today as young will have only been formed less than 1 billion years ago. So stars that have formed that recently in cosmic time tend to be have a reasonable population of a reasonable amount of these heavy elements in their makeup. So our sun is an example of this, really. Okay, so it's got the sun has about 2% metals by mass, and again, so metals here means everything heavier than helium. And so you would use the term metal-rich for these population 1 stars. Okay. So again, none of these numbers are hard and fast, but they're just orders of magnitude. Okay. So this is population 1 stars, young metal-rich stars. And so because they've formed recently, then often there will be, they will be in regions where stars are clearly still forming and keep forming. Okay. Nothing static out there. Stars are constantly being born and stars are constantly dying. Okay. So there is a dynamic equilibrium out there in the galaxies. Okay. And of course, we've already met examples of these population 1 stars because these characteristics are typical of open clusters. Okay. So the stars in open clusters are still young. So often hardly any of the stars will have evolved off the main sequence if they're this young. If they're a billion years, then some of the stars will have evolved into sort of supergiants or red giants, but not many. Only the most massive ones would have evolved. And if you take a spectrum of these stars in open clusters, then you find that they have a lot of these quite strong lines due to the heavy elements. And in clusters like the Pleiades that I showed you earlier, then you can still see the sort of gas and dust left over from the recent formation of the cluster. So that's population 1, okay? And open clusters are an example of those. Now let's talk about population 2 stars. Okay? So as you can imagine, these are the kind of opposite of population 1. So they're very old, so 10 billion years typically. And a good number to keep in your head here is the idea that the universe itself is only 14 billion years old from what we understand about cosmology. Okay, so these stars, population 2 stars, are nearly as old as the universe itself. So again, this is the idea that they were some of the first stars formed because they formed a long time ago, back much closer to the Big Bang than we are today in time. And because they formed soon after the Big Bang, there had not been time to build up a lot of heavy elements because there hadn't been previous generations of stars to make those heavy elements. So these sort of very early stars that formed in the universe are all metal poor. They hardly have any heavy elements in them at all when you look at their spectrum. So again, there's a big range here, but a factor of 10 less metals than stars like the Sun. But there are even stars with sort of 0.0001% metals in them. In fact, it's a bit of a competition in astronomy to find the most metal poor star, basically a star that's made of pure hydrogen and helium, because if you do find those really, really metal poor stars, then in effect you are directly probing what was left over from the Big Bang, and those kind of stars are used to then test the Big Bang theory itself. Not Sheldon, but the real Big Bang. So these population 2 stars, because they're so old, they formed a very long time ago. Usually there's no signs of star formation anywhere near them, so there's no gas or dust anywhere near them. Again, this will become a bit clearer later on in the module. But just like with the population 1 stars, where we've already seen that open clusters are a good example, globular clusters are the perfect example of population 2 stars. They are incredibly old. There are hardly any main sequence stars, any massive main sequence stars left. They've all evolved off. Okay, so the only ones left are very low mass main sequence stars. And if you look at their spectra, you hardly see any heavy elements in there. Okay, so let me just summarize what we've learned in this lecture. So we started with color magnitude diagrams for star clusters, and hopefully you're already getting the idea that you can use them to determine their age by basically how far down the main sequence have they burnt. Okay, and don't forget the main sequence is a sequence in mass, and therefore it's a sequence in age, because as you get to lower and lower masses, their main sequence lifetimes get longer and longer. So they can be used as clocks. And because of that, they are a key tool in the study of stellar evolution, and more widely, in a sense, in the study of how whole galaxies work and evolve over time. Because they really pretty much are our only clocks out there. So we need to find these clusters so that we can get a handle on how different parts of galaxies, how old they are, what's happening in time. And as we've just been discussing, then again, this will come back. We'll come back to look at this when we talk about the makeup of whole galaxies. We've got whole collections of stars, but you can divide these kind of different populations of stars into old metal-poor stars, which is the population 2, and the young metal-rich stars that are population 1. Okay, so that summarized the lecture. Just to, again, give a little insight into a little bit of time, perhaps. I showed you a nice picture of one of those partial nebulae with the cloud of gas that's been ejected from the outer envelopes, the material that's been enriched in heavy elements by the fusion reactions that have been going on in the star over its lifetime. All that material is now being ejected into space. So the Planetary Nebula, as I mentioned, they're coasting, or the material is coasting away at a more sedate speed of 10 kilometers per second. So that's much slower than the supernova explosions, which are much more violent. But even for these, then we'll soon see that in terms of cosmic time, then the material gets returned out into space fairly quickly, ready to be turned over into the next generation of stars. Okay, so I'll leave you with that little problem. Simple enough. So how many years? So give me the answer in years. How many years before material that's traveling at 10 kilometers per second basically travels a distance of 1 parsec, which is the typical separation to the next star, okay, just to give us some kind of measure here. Okay, so we'll stop there. We'll see you next time.